Okay, let's dive right into this explainer because today we are fundamentally shifting how we think about AI training. For the longest time, the industry has basically treated training as a brute force scale problem, right? You just pour in more data, stack up more GPUs, and kind of just wait for the model to get smarter. But the paper we're unpacking today, Compute is Not Learning, introduces this incredibly fascinating energetic paradigm, or EP architecture. It totally reframes training from this blind dumping process into a really delicate energy conversion problem. We're going to see exactly why throwing more data and more compute at a model absolutely does not automatically equal more learning.
And I love this quote because it perfectly illustrates our core thesis today. Dumping massive amounts of data into a model without actively controlling the learning boundaries, you're essentially just building a giant compute incinerator. Think about it. Compute, data, gradients, memory, all of this is energy. And that energy has to be carefully, deliberately converted into actual model capability. If your conversion pathway is sloppy or poorly controlled, you're literally just burning expensive activity while the model's actual competence barely even moves.
So here is our roadmap for the explainer. 1. The training energy crisis. 2. The cognitive boundary concept. 3. 4 gates of control. 4. The EP training loop. And 5. Rise of the cognitive architect.
Let's kick things off with Section 1, the training energy crisis.
So, let's start with the fundamental problem that plagues massive models. Now, if you follow AI development, you're totally familiar with a loss plateau. But usually, we just treat it as a minor optimization inconvenience, right? Like a little speed bump. Well, the EP framework changes this framing entirely. A loss plateau is actually a structural failure in the training energy system. Your model is still eating up all that expensive compute, but that active compute consumption is no longer converting into proportional capability gain. The system is incredibly active, sure, but the conversion rate has basically flatlined.
So what's actually driving this collapse? Well, there are two primary forces at play here. First up is power law decay. This is just the mathematical reality that as a model gets smarter and more mature, ordinary data simply becomes way less informative. The errors that are left over are super rare and complex, so just applying uniform compute gives you massive diminishing returns. And the second force is the information bottleneck. A mature model already has a pretty solid compressed worldview. It has to spend valuable energy just deciding if incoming data is redundant or conflicting or completely trivial. Sorting through all that useless data totally clogs the bottleneck and just wastes your precious compute.
Moving on to Section 2, the cognitive boundary concept.
Okay, so to fix this massive energy leak, we need to locate the precise spatial edge where actual learning happens. And this brings us to the core architectural principle of this whole paradigm, the cognitive boundary. This is the precise region where training material is difficult but still reachable. It sits right on the razor's edge between what a model has already mastered and what is just so completely complex it can't absorb it yet. The real goal of efficient training isn't just maximum exposure to data. It's continuously tracking this exact boundary. It helps to visualize this as 3 distinct zones. If the data is too easy, well, the model already gets it. The gradients are super weak, and your compute is just completely wasted. So the system action, skip it or downweight it. Now, if the data is too hard, it's not learnable yet. It just produces noisy, destabilizing gradients because the model doesn't have the foundation to grasp it. The action there is to defer it. But then you have that perfect sweet spot, the cognitive boundary. That's where you get maximum information gain. The data here pushes the model across its next frontier of understanding without breaking the competence it already has. So you prioritize that and assign strong learning energy to it.
Let's look at Section 3, 4 gates of control.
Let's see how all of this theory actually builds into a real architecture using 4-dimensional control gates. Instead of a blind pipeline, EP uses this highly coordinated chain. At the very entrance, we have to stop and ask a really critical question. Which batch of data is actually closest to the model's current cognitive boundary, and which one is going to give us the absolute highest capability gain per unit of compute?
And that brings us to our very first gate, GRETS. Conventional training basically treats a dataset like a fixed, dumb queue. The model just blindly eats whatever is next in line. GRETS totally flips this by using gradient-based estimation to actively select high-value batches. It literally turns the dataset from a passive pile of inputs into this controlled energy field, actively routing data right into the learning boundary at the exact moment it's most useful.
But as you can probably guess, document-level selection is often a bit too coarse. I mean, a document might have 2 brilliant high-value sentences completely surrounded by useless boilerplate filler. So once a batch makes it through that first gate, we have to look closer and ask, does every single word,
every single token actually deserve our processing energy.
And that's exactly where token skipping acts as our second gate. It tightens the control granularity to stop useless tokens from quietly acting as hidden cost centers. Think about it. Redundant tokens take up space in the context window, they consume attention, and they dilute the gradient flow. By aggressively filtering them out, a really small, high-value, dense slice of data can actually significantly outperform a massive full-stream training run.
Okay, so now we have this beautifully high-density, perfectly targeted information inside the model, but we're not done. Now we have to ask, is updating every single parameter in this massive neural network all at once really the smartest way to spend our energy?
The answer is a definitive no, which leads us to gate number 3, Lisa. Updating everything all the time is wildly expensive, and worse, it risks overriding those useful, stable structures the model has already learned. Lisa is essentially a surgical intervention. It freezes most of the layers to keep things stable, and it concentrates the learning energy strictly on the specific layers that actually need to adapt. This concentrates the signal, it protects the memory from catastrophic forgetting, and it enforces serious compute discipline. You're only spending energy where movement actually matters.
Finally, after that surgical update happens, we need to check the receipts. We have to evaluate the result. Has the optimizer built durable, generalized competence, or did it just memorize a highly brittle configuration that's going to totally shatter under pressure?
Enter our fourth and final gate, SAM, or Curvature and Escape Control. See, sometimes the model finds this sharp, narrow little basin in the lost landscape. It looks successful locally, but it's a trap. It's incredibly brittle. SAM comes in and actually penalizes these overly sharp solutions, essentially forcing the model to escape into flatter, broader, more stable regions of the lost landscape. It guarantees that the learned state is actually robust under disturbance, not just memorized perfectly for one specific, narrow training path.
Now for Section 4, the EP training loop.
Now, these 4 gates we just talked about, Greats, token skipping, Lisa, and SAM, they aren't just isolated party tricks. They form one seamless, coordinated governance system. The first half of the CP training loop is all about diagnosis and routing. It starts by diagnosing why the system is stuck. Is it choked on redundant data, or is the data too hard? Then, it locates that exact edge of competence, the cognitive boundary. From there, it dynamically selects the absolute highest gain batches and aggressively filters out the low-value tokens.
Then the second half of the loop takes over for execution and validation. It executes the surgical parameter updates through Lisa, audits the curvature to force an escape from any of those brittle minima via SAM, and then it strictly validates that the compute was genuinely converted into stable capability. Finally, it stores the boundary map for the next cycle. It's this beautiful, continuous, self-correcting feedback loop entirely designed to maximize actual learning per unit of energy.
And finally, Section 5, Rise of the Cognitive Architect. This energetic paradigm entirely changes the job description of a frontier AI developer. We're talking about a massive professional transition here. In the old model, the engineer was basically a compute laborer, just shoveling more and more data into the furnace, running it longer, leaning entirely on blind scaling. But under the EP model, the engineer is a cognitive architect. You are no longer just feeding the machine. You are meticulously designing the exact conditions for efficient learning. You are actively managing adaptive routing, surgical updates, and stability-aware optimization. It's a completely different game.
Now, a quick but absolutely crucial side note for our explainer today. We've explored the public conceptual framework and the overarching architectural principles of EP, but the proprietary internal controller logic, the specific code-level algorithms, and the private scoring rules powering this system are entirely undisclosed in the source paper. We don't have those secrets. But honestly, the public principles alone represent a profound shift in how we need to approach training efficiency.
And that leaves us with this incredibly provocative final thought straight from the paper. The next frontier of AI training isn't just hoarding more compute. It is the architecture that prevents compute from becoming fire. So ask yourself, does the future of AI really belong to whoever simply owns the largest mountain of GPUs? Or does it belong to whoever can actually convert the highest fraction of that compute into real, stable capability without just burning it all away? Keep that in mind the next time you see a massive new model announcement. Thanks so much for joining me on this explainer, and we will see you next time.